Now let's see the magnetic field due to a toroid. Generally, toroid means copper wires are tightly wound over a ring, okay, which is shown in the figure, the left side of the slide. Okay, this is the toroid. Over a ring, copper cable is wounded. Okay, generally it is having n turns and carries a current I. Now let's calculate the magnetic field density due to the toroid at outside the toroid and inside the toroid. Okay, so from this let's try to form an Amperian path for the toroid. Okay, so this is the top view of the toroid. Okay, so here you are having the wire wounded like this. Okay, and in the iron core you can form the Amperian path. The red one is the Amperian path, and the field will be a circulating one. It is H here. Okay, the dimension of this is 2a, and the radius is rho. For the Amperian path, the rho is radius. Okay, now a toroid whose dimensions are shown in figure as n turns. Let's assume the number of turns is n, and it carries a current I. Okay, so the Amperian path in the circle is circle, and it is having a radius rho. Okay, since the n wires of the toroid encircles this path, and each path is carrying a current, so the total current enclosed by the Amperian path is n wires. Okay, each turn carries a current I, so total n turns, so the total current will be Ni, that is enclosed by the Amperian path. So total current is Ni. As per Ampere's circuital law, line integral of H dot dl is I enclosed, that is H 2 pi rho. Okay, H into 2 pi, the line, this is the uh, circumference of the circle Amperian path. Okay, so H dot dl, H into 2 pi rho, directly you can write. Okay, that is equal to Ni. Okay, from this you can write H is Ni by 2 pi rho for the region rho naught minus a to rho naught plus a, where rho naught is the mean of the radius. Okay, and using approximate value, you can form H approximate is Ni by 2 pi rho naught. So Ni by L. Outside the toroid, the current enclosed by Amperian path is Ni minus Ni, that is 0. So the field outside the toroid is equal to 0. So for the region, H vector is Ni by 2 pi rho. Okay, outside the region it is 0. Now let's have a problem based on the toroid. Okay, a toroid of circular cross section whose center is at the origin and the axis the same as z-axis has 1000 turns with rho naught equal to 10 centimeter and a equal to 1 centimeter. If the toroid carries a 100 milliamperes current, find magnitude of H vector at 3 comma minus 4 comma 0 and 6 comma 9 comma 0. So as per the previous derivation, H vector is Ni by 2 pi rho, Ni by 2 pi rho, Ni by 2 pi rho. Okay, uh, here Ni by 2 pi rho, and here rho naught is given, that is 10. Okay, and the point is given 3 minus 4 comma 0, 3 comma minus 4 comma 0. Okay, so the row is running from 10 is 1, a equal to 1. Okay, so here you are having Ni by 2 pi rho, which is for the region rho naught minus a to rho naught plus a. Rho naught is 10 minus a 1. Okay, so 10 minus 1 2, 10 plus 1. Okay, so 9 to 11. Okay, that is Ni by 2 pi rho is for the region 9 to 11. Okay, and 0 otherwise. Now let's calculate the point rho. Okay, that is 3 centimeter minus 4 centimeter and 0, and the distance rho is square root of 3 square plus 4 square plus 0 square. So 9 plus 16, that is 25. So square root of 25 is 5, which is less than 9 centimeter, which is less than 9 centimeter. Okay, so only in this region 9 to 11 you will have this field, otherwise it is equal to 0. So the point is outside the region, so the net field in this point is 0. And the second point, that is 6 9. Okay, 6 square plus 9 square plus 0 square, square root of 117, that is 10.81, which is less than 11. So you can apply the formula Ni by 2 pi rho. So N is 1000. Okay, N is 1000. I 100 milliampere, that is 110 power minus 3 divided by 2 pi into rho, that is square root of 117. Okay, if you substitute this, you will have 147.1 amperes per meter. So the field at point 3 minus 4 is 0 is 0 amperes per meter, and at point 690 it is 147.1 amperes per meter.